I'm going to buy myself a piano and relearn how to play it so I can have some music over this as an intro, but hey, ain't that pretty? It's actually just one day on repeat, so there's no point in watching that for long. I actually wanted to talk about this intro, which does have noise. No, I didn't. I wanted to talk about the video that followed that intro. Now, it's not for me, it's for Dud Mumble, but I thought I'd try it anyway. Yada yada, this noise got annoying after a while. There's a whole lot of this script and there's very little footage. Right, let me just jump back. There we go, a round object at an unknown distance. So that's one screenshot. That. And then about 10 seconds of this in a 2.5 minute video of other stuff. There's a known distance and an object of known size, assuming that is a centimetre ruler, and a known movement. Rotate angle and zoom. We're assuming something here about it moving exactly right angles to the line of view. And get on with it. There we go. That's all he wants. So I screwed this up and then realised what I'd done, and I think I got it right. I made an animated GIF. It was late at night. I didn't want to be talking, and tired and didn't want to talk to anyone. So there's a screenshot. Now I did convert this to GIF. So if I pick a spot and zoom right in, you'll probably notice it's stripy. It's stripy because it has been converted to a GIF with a 256 colour palette, rather than being the full 2 million colours or whatever you get on a monitor. But from that screenshot I can take a measurement, which is right here. Just zoom. Why is it not zooming in? Because I haven't clicked this window. GNU image manipulation project cares which window you last clicked, and buttons do different things depending where the mouse was. Not where the mouse is, but where you last clicked. 96 pixels wide, which puts the central pixel of that ball at 1262. Now if you look around the edges of that ball, you can see it's kind of fuzzy. This could be Rayleigh scattering. You know, that funny interference pattern effect. It could be a less than perfectly clean lens on the camera that filmed this. It's got a dark background, so it's probably not light from the ball reflecting off that, especially given the angle of the light. But we also have this problem that there are individual pixels. I mean, it's going to get really obvious if I zoom into stupid levels. Like, which of those pixels is the edge of the ball? Presumably the edge of the ball goes through these pixels, somewhere here. But I can only really say to the nearest 1 pixel where the edge of that ball is. So I've got a ball diameter of approximately 96 pixels. 96 pixels to the nearest pixel, not 96.000 pixels, you know? It's two significant figures there. Okay, the next thing we got is this screenshot. I'm taking his word for it, that's the distance, and I'm making the assumption that this is a metric ruler and that these are centimetre marks and millimetre marks. On that screenshot I can also take measurements. Very spidery thin green script. Roughly where the ball was in the previous shot, which I can kind of show you by doing... Good grief. Oh, it's because it's in GIF mode, it can't actually do transparency anymore. Before I converted it to GIF, I could show you by making it partially transparent, but hey. Roughly where the ball was, about here. About 1212, was it? And again, just typing the plus into the opacity meter rather than zooming in. There you go. Pixel counts of the 2mm marks, so 112.2 and 112.7 centimetres and 113.2, 111.7 and 11.2. 5mm apart on the ruler is 85 pixels, and then just 84 pixels. And way over to the left, a whole centimetre apart, is 169, which is 85 plus 84. So it's somewhere around there. Centre of field of view. Obviously, if this ruler is exactly in front of you, you're looking at it square on there. Let me rephrase that. If that ruler is exactly in front of you and you're looking at it square on there, you're looking at it at a bit of an angle over here, and it's slightly further away, so you would expect that to be less than 170 pixels. Less than twice that 85. Oh boy. Yeah. Considering this is, you know... I've got several pixels per black mark there, but still the ball was only to the nearest, you know, only the 2 sig figs. We got that distance, I'm taking his word for it. 128.6 centimetres. Given that we know that 1 centimetre there is 170 pixels, or 5 millimeters is 85 pixels, assuming you're looking square on out that ruler, then you have a right angle triangle. From you to that mark where you're looking square on, there's a right angle there, 85 pixels to the left, there's some angle there, it's damn nearly a right angle, then there's a hypotenuse from there back to your camera, subtending a tiny little angle at the camera, whose tangent is 5 millimeters divided by 128.6 centimeters, which is 0.0039 radians. So, for those who don't know, you know, there's 2 pi r radii to a circle. Well, there are 2 pi radians to a circle. So if you have a 10 meter rope stretched tight between you and a gatepost and you walk 10 meters, you have gone 1 radian of the way around a circle centered on that gatepost. Radians are useful for some calculations. You may be more familiar with degrees. There is an easy way to convert. Kind of cheesy. There are 2 ways to convert. One, if you want to know what, say, 50 degrees is in radians, well, you can divide it by 360 and then multiply by 2 and then multiply by pi, or just divide by 180 and multiply by pi to get 0.872665 radians. The alternative would be 50 in degrees sine, switch to radians, inverse sine, 0.872665. Right. I've got this number, which is of course 5 millimeters divided by 1286 millimeters is the tangent of what angle? It is the tangent of 0.0388800529211977 blah blah blah. Okay. Radians, also known as 0.0039 radians. Of course, 2 sig figs is good enough, right? From that, because we know the angular size of the ball is 96 pixels, no, yeah, 85 pixels is 85 pixels represents that angle. 96 pixels for the ball represents 96/85ths of that angle. Times 96 over 85 is 0.044 radians. Close enough. Just keep that number aside. Third screenshot, at which point I should zoom out so you can see it. Dollies the camera at 150 centimeters right and doesn't really leave it for very many frames. If I've got a big complaint about the video apart from the noise, it's that he could have given us a couple of seconds of steady footage from after that move. Anyway, there's your ball again, obviously, and it was over here, it is now over here. Significant thing that we don't, well, potentially significant thing that we don't know. Is he showing the full field of view of the camera, or is this cropped from it? Was the ball at the centre of the field of view, or not? That could matter. Anyway, more measurements. Measurements on that ball. 98 pixels wide. Maybe I chose a different level of opacity. Maybe because the camera was now looking at that white board rather than at a mostly black square, the camera changed its exposure settings, which caused a little bit of bloom on that ball. You can see the halo is less visible around it now. Well, I don't know, I mean, I'd have to get a really good look at the original footage and probably reproduce it with several different cameras to be sure about this stuff. But anyway, we have got a centre position 504. Now I did copy these two coordinates from the ruler screenshot, just straight copy from one layer to the next, and start calculating exactly how many millimetres across that bit of the ruler it was, and then I thought, screw that, I went across here. 1286 is where the centre of the ball was, 504 is where it is now, it has therefore moved 758 pixels. Right? And we know from previous calculations that whatever that bloody number was, 0.0039 pixels, was it? That 85 pixels is 0.0039 radians. So if we get that 758, divide it by 85 and multiply it by the angle with a tangent of 5/1286, we get the angle through which that ball has moved in the field of view due to the camera moving sideways. If you want to imagine this one as a top-down view, draw an N shape. That angle is in the top left and in the bottom right, between the angle diagonal line and the verticals, the sides of your drawing. And the distance moved, the 150 centimetres, is the width of the drawing, and the distance to the ball is the height of the drawing. So we have that angle, which we know to be the tangent of 150 centimetres divided by the distance. Which means that the distance is, well, take the tangent of that angle and then divide it by 150 centimetres and press the 1 over x. And you get 43.25 metres. Now that we know the distance is 43.25 metres, it's probably so much easier to read if I zoom out just a little. And we know the angular size of the ball in the original picture. We know that the angular size of a ball is the sum of two angles, each subtended by the radius of the ball at the point of a triangle. Radius of the ball with the hypotenuse from the camera to the centre of the ball, and the adjacent from the camera to the edge of the visible part of the ball. And because we're talking opposite over hypotenuse, it's sine, not tangent. Use tangent for bricks. Not that there's much difference with tiny angles like this. So the sine of half the angular size is the ratio of the radius to the distance. And we've just calculated the distance. So if we rearrange this, we find a radius of 94.95 millimetres. Multiply that by 2 times pi, and the embarrassing thing is I forgot the 2 times first time I did this. I just multiplied by pi like a fool. Gives us a circumference of 596.6 millimetres. So, forget the rest of it, just copy that bit. There's my answer, including how I got it. Here's hoping I'm right.